Good evening one and all. First and foremost, I'd like to thank Department of Physics and our teacher Dr. C.P. Khatiwala of Namchi Government College and also Sikkim University for providing me such a platform to make a video for the partial fulfillment of BSc Honours on Physics at 6th semester from February to July 2021. My name is Barsha Chitri with roll number 18NS0029 and today I'm going to talk about my topic Raman effect or Raman spectroscopy. And my topic is Raman effects or Raman spectroscopy. And in this topic, I will be mainly talking about quantum theory of Raman effect, Rayleigh, Stokes and anti-Stokes line. So now we'll be discussing the basic principles of Raman spectroscopy. We know that light possesses many interesting properties. Light has the property of reflection, refraction, diffraction, etc. Scattering is yet another interesting property shown by visible light. So, when a monochromatic beam of visible light passes through a non-observing medium, most of the light is transmitted, but a small fraction gets scattered by molecules in all directions. Most of the scattered light will have the same frequency as the incident light, and this is known as Rayleigh scattering. The term Rayleigh scattering was named after Lord Rayleigh, who first observed the phenomenon of scattering of light. We have seen that most of the scattered light will be having the same frequency as that of the incident light, but in addition to Rayleigh scattering having the same frequencies, it was observed that some scattered radiation are having frequencies different from that of the incident light. That is, they may be having greater or lesser frequencies than that of the incident light. And this phenomenon is referred to as Raman scattering. And this observation was made by the Indian physicist Sir C.B. Raman along with K.S. Krishnan in 1928. And Sir C.B. Raman was awarded the Nobel Prize in Physics in 1930 for the discovery and study of Raman scattering or Raman effect. So, what is Raman spectroscopy? The spectral method developed on the basis of Raman scattering or Raman effect is known as Raman spectroscopy. And this spectroscopy technique is used in both physics and chemistry to study the vibrational, rotational and other low frequencies modes in a system. This method lies on the Raman scattering or inelastic scattering, where we'll discuss about an elastic scattering later. So this method relies on the Raman scattering of monochromatic light by molecules, usually from a laser in the visible, near infrared or near UV range. So let's take the help of quantum theory to understand the origin of Raman scattering or Raman effect. We know that according to quantum theory of radiation, electromagnetic radiation consists of particles or photons of frequency mu and energy h mu. We can imagine that the photons and energy are undergoing collision with the molecules. There are two ways in which the radiation or photons can be collide with the molecule. One is elastic and the other one is inelastic collisions. Let's see what is the difference between elastic and inelastic collisions. In elastic collisions, there is no net gain or loss of energy by the molecules. So, when a ball hits a rigid wall, it just bounces off without any loss of energy. This is an example for an elastic collision. So, when there is no net gain or loss of energy by the molecule, we can say that the scattered radiation will be having the same frequency as that of the incident radiation, or mu s equals to mu I, where mu s is the frequency of the scattered radiation and mu I is the frequency of the incident radiations. And this is referred to as Rayleigh scattering. Since there is no gain or loss of energy, the energy of the scattered radiation will be equal to that of the incident radiation. So that change in energy is equal to 0. That is delta E equals to 0. This is the case on elastic collision. Now let's see what is meant by inelastic collision. If the collision is inelastic, there will be the energy exchange between the molecules and the incident radiation. So to understand what is inelastic collision, let's take an example. In elastic collision, we have seen a ball striking a rigid wall. So here, instead of striking a rigid wall, if a ball is striking on a drum, then the ball hits on the drum. The drum starts oscillating at its own frequency, or the drum may vibrate. So that energy will be exchanged with the ball. So here that occurs an energy exchange between the oscillating drum and the ball. So this is an example for inelastic collision. If there is an energy exchange between the molecule and the incident radiation, then the frequency of the scattered radiation will be different from that of the incident radiation. Or mu s will not be equal to mu I, and this is referred to as Raman scattering. Since there is energy exchange, the energy of the scattered radiation will not be equal to the energy of the incident radiation. So delta E is not equal to 0. That will be positive or negative depending on how the energy is exchanged between the photons and the molecules. That is, whether photon is giving its energy to the molecule or whether the molecule is giving its energy to the photon. Depending on that, the value of delta E will be positive or negative. So this is called inelastic collision. Now let's see how different lines occur in the spectrum. In the Raman experiment, a monochromatic beam of light, usually occurs in the visible region, is allowed to fall on the same tone, and we measure the scattered light with the help of a spectrometer. Now, when the photon interacts with the molecule will get excited from the lower state to the higher energy state, and it will come back to either the original state or a different state. Since the source of radiation is in the visible region, usually it's in the visible region, and there will be transition in the electronic levels. So that is represented as S0 here. So that is the electronic ground state. And we know that in each electronic energy levels, there will be various rotational and vibrational energy levels. So here, for our convenience, we are representing only the vibrational energy levels. So S0 denotes the ground electronic state. In that ground electronic state, there are different vibrational levels. And if there is S1, so that will represent the first excited electronic state. And in that first excited electronic state, there will be various rotational and vibrational levels. So in order to explain the Raman scattering, we are representing only the vibrational energy levels in the ground electronic state. So suppose a photon of frequency mu I and energy h mu I collides with a sample having energy e mole, and that light is scattered with the frequency mu s. Suppose the energy of the molecule after collision is E dash. Collision can take place in two ways: elastic collision and inelastic collision. So let's consider the first case, which is the elastic collision. Here we have already seen that in inelastic collision there is no net gain or loss of energy by the molecule. The frequency of the incident and the scattered radiation will be the same, and that is referred to as Rayleigh scattering. So let's see how the molecule will undergo transition in Rayleigh scattering. The molecules will be initially in the lowest vibrational level, which is the ground level, depicted as V equals to 0. So from V equals to 0, the molecule is excited to a virtual higher energy state, and then it relaxes and returns back to the original ground state, that is V equals to 0 to V equals to 0. That means there is no net gain or loss of energy during this transition. Since it returns to the same energy level, then the change in energy E dash minus E will be 0. That is equals to 0, and this results in the Rayleigh line. Now, the second type of collision is inelastic collision, and here we see that in inelastic collision there will be energy exchange between the photons and the molecules, and the change in energy of delta E will be positive or negative depending upon the energy exchange. When the incident photon collides with molecule, and if the photon gives some of its energy to the molecule, that is, the incident radiation while colliding gives its energy to the molecule, then the scattered radiation will be less energetic, and such radiation is called Stokes radiation or Stokes line. So here in Stokes line, the molecule initially on the ground vibrational state will be excited to a higher energy state, but relaxes back to higher energy level than the original level. So what happens? The frequency of the scattered radiation will be less than that of the incident radiation. And since the molecules gain energy, E dash minus E will be equal to delta E greater than 0. That is, delta E is negative. So in Stokes line, the molecule relaxes from the virtual level to a higher level than the original one, so that delta E is positive. Now, If the incident photon takes energy from molecules during collision, then the scattered radiation will be more energetic because it has taken out some energy from the molecule. So the scattered radiation is more energetic, and that is known as anti-Stokes radiation. So since the scattered radiation is more energetic, we can say that the frequency of the scattered radiation mu s is greater than mu I. The transition will take place from the first vibrational level V equals to 1 to the ground vibrational state V equals to 0. That is, the excited molecule relaxes from the virtual level to a lower level than the original. So the change in energy will be E dash minus E, that is delta E less than 0. That is delta E is negative, and this will give rise to an anti-Stokes line. So the change in energy will be E dash minus E, that is delta E less than 0. That is delta E is negative, and this will give rise to an anti-Stokes line. So this difference in frequencies of the Rayleigh line and the Raman line is referred to as Raman shift or Raman frequency, which is usually denoted as delta mu equals to mu I minus mu s. Delta mu is the difference in the frequencies of the incident and the scattered radiation. The Stokes and the anti-Stokes line are generally known as the Raman lines, and that will be situated on either side of the Rayleigh line, as you can see in this image. So the frequency of the scattered radiation can be represented as mu s equals to mu I plus minus delta mu, and here plus sign represents anti-Stokes line and minus sign represents the Stokes line. The Stokes line will appear on the lower frequency side of the spectrum, whereas anti-Stokes line will appear on the higher frequency side of the spectrum. So we have seen that Stokes radiation occurs at lower energy than the Rayleigh radiation, and anti-Stokes radiation has the greater energy. So this increase or decrease in energy is related to the vibrational energy levels in the ground electronic state of the molecule. Since we are considering the transition between vibrational and energy levels, the observed Raman shift of the Stokes and anti-Stokes features are a direct measure of the vibrational energies of the molecule. So for a given substances, the Raman shift, that is delta mu, is a characteristic of that substance and is independent of the frequency of the incident radiation. We have seen three different lines in the spectrum, that is Rayleigh lines, Stokes lines and anti-Stokes lines. So among these three lines, which will be the most intense one? There are several factors which affect the intensity of the spectral lines. The most important one is population of the energy levels. Population means what is the number of molecule in each energy level. Greater the population means greater will be the number of molecules that is available for excitation or relaxation. So greater the number of molecules, the greater will be the intensity of the spectral lines. So let's first consider the Rayleigh line. We have seen that in Rayleigh line scattering, the molecule is excited from the ground vibrational state V equals to 0, and it returns back to the original V equals to 0 state. So at ordinary temperature, most of the molecules will be in the ground state. That means the population of the ground state will be higher. Also, the ordinary temperature, the molecule will most probably relaxes back to the ground vibrational state. So that means this transition V equals to 0 to V equals to 0 will be the most probable one, and hence Rayleigh scattering will be the most intense. So the occurrence of the Rayleigh scattering is much more probable than Raman scattering, and hence the Rayleigh line will be the more intense than the Raman lines in the spectrum. Rayleigh line is the most intense one. So what about the others, Stokes or anti-Stokes lines? So first let us consider the Stokes lines. The molecule is excited from a ground vibrational state, and definitely the population is greater, but it relaxes back to the higher level. Whereas in anti-Stokes, the molecules is excited from a higher vibrational level and it is returning back to lower ground vibrational state. Then Number of molecules possessing higher energy will be less compared to the number of molecules in the ground state, because molecules always prefer a minimum energy state, and hence the population will be greater in V equals to 0 compared to V equals to 1. And as a result, Stokes emission is more favored than anti-Stokes emission. In another word, Stokes line will be more intense than anti-Stokes lines, and the intensity of these three lines varies in the order Rayleigh greater than Stokes greater than anti-Stokes lines.